Obligatory sip of coffee. All right. Now, the thing today, January 31st, 214, so lecture 3. All right, hold on. Menu, iris, manual, menu, zoom, open just a touch. Okay. So last week, we had, oh, it is, oh, dang it. That cross is just so that it can focus on something. Okay. So with these charges, you know that like charges attract. The ones on the left are 1, the ones on the 2 are right. So this is the force on 1 by 2. This is the force on 2 by 1. Oh, because I'm an idiot. All right. Now it's fixed. Dang. All right, it's 8:07. Let's just... So now these are like charges and they repel. There was one time, honestly, I sat here in front of the class, I was getting mad. How come the class could not understand that -1 times -1 is -1? And then a little part of my brain was like, hold on, just come back, Dr. Eschenberg. So these show the directions. Now, the magnitude of all of these things are determined by Coulomb's law. And F is K Q1 Q2 over R squared, where R is the distance between the two charges. Q and Q1 and 2 are the magnitudes. It is always, positive. And Coulomb's law gives magnitude only. So we have in the past, like last week, Coulomb's law is used in the creation of the force, can't spell, can't add, I'm doomed, force vector. So when we have, like say, A newtons at B degrees, the Coulomb law determines this, and the B part, student observation and trig. So Coulomb's law plays no part in the direction of that force. You determine the direction of that force through observation, basic knowledge of trig, that kind of stuff. So in the case like this, You say, well, those are same charge, so they repel. So the force vector on 1 by 2 is pure left. The force vector on 2 by 1 is pure right. And so in a simple situation like this, you can immediately determine that this comes from this. The theta for this is 180. The theta from that is 0. You look at it. Now here, they're dislike charges, so they attract. These, let's say they were all of the same magnitude. Coulomb's law would say that they all have the same magnitude, but now they are of differing charge. So F12 is now at a theta of 0 degrees, and F21 is at a theta of 180. Coulomb's law didn't change. The charge magnitudes were the same, the distances were the same. All that changed were the polarity of the charges. Your knowledge of like charges repel, dissimilar charges attract, that determines the direction. So in something that's a little bit more complex, one, two, three. And the exercise is to simply describe the net force on 1 from the other 2 charges. Well, the force on 1 by 2 must be down. So they are of they're not same polarity or same charge. So it pulls down. The theta here must be 270. And so we work from that. Now, the negative, it is a repulsive force. So it is up and to the left. So the force on 1 by 3 is up and to the left. I miswrote this one a little bit. The force on 1 by 2 is straight down. Now, one of the questions that we have is, well, how do you get the direction? And what you kind of do is you build just your little bit of trig. And this angle here, because this line and that line cut through the charge, that theta is the same as this theta. And that theta is what we would want. And let's say, for the sake of argument, that this is x and that is y. So this is r. R would simply be the square root of x squared plus y squared. Or you could, since in Coulomb's law we use r squared, you could just say the value of r squared is x squared plus y squared. So that r squared, or I'm blah, get rid of that. So r squared is just x squared plus y squared. And this theta, which then becomes that theta, is just the inverse tan of opposite over adjacent, or y over x. So what I'm really trying to do is teach you just the generic procedure on how to get the angles, how to determine the angles, and to get the distances. And we've gone over on the Thursday lecture, and so we're not going to do it again. just the techniques on how to add forces from vector perspective and go from there. Now, we've covered Coulomb's law, but what we haven't done yet is talked about the electric field. We need a way of describing what is that point in relationship to that electric charge like. And the electric field is K big Q over R squared, where the Q is the charge of the point, and it is also a magnitude. And then this is the distance between the two. Like the Coulomb's law, or like Coulomb's law, E is positive. So you cannot have an electric field that's negative. And this electric field value is the magnitude of the electric field vector. An electric field this is used like Coulomb's law. In the creation of the electric field vector. The electric field vector looks the same like the electric field or the force vector, with one notable difference. The unit for E field is newtons per coulomb. And this that determines that part, and once again, student observation and trig determine the next part.
Where do you get the unit from?
Very good question. Now in let me talk about the force is KQ1 Q2 over R squared. And electric field is KQ over R squared. And what you can do is you can substitute the electric field, the KQ over R squared, with this. Because initially in this equation, if we have two charges, Q1 and Q2, and then I take away Q2, there is an electric field there caused by 1. Really, what the force, Coulomb's law is that the force is equal to the electric field at a particular point times the charge that you put on that point. So if I put a Q2 here and the electric field is a particular value, then it is going to experience a force. And so you can rewrite this F over Q2 is equal to E. The unit for force is Newton. Unit for Q is Coulomb. So this is one of the ways where you can get, well, what are the units for electric force? Now, one of the things that we got to start thinking about is, fortunately, I've been left props. So if we have pink is positive, white is negative. So they feel forces. And so naturally, if I let these things go, they would start, and there was no friction, they would start sliding at each other until they came together. But let's say I had this charge here and no charge here. I would want to know, hey, if I put this charge there, how would it move? And one of the things that you can do is you can first say, well, what's the electric field like because of this charge? It now begins to get to a point where you're having to start to visualize what electric fields look like. If you've ever walked across the floor, you've built up a static charge, you're kind of walking over something, towards something else that's charged, and you feel the hairs on your arm start to raise up. When you start to reach for the doorknob and you feel, there's kind of like a sizzle that you feel on your fingers. What you're doing is you're moving through an electric field and stuff is about to happen. So you need to kind of visualize how, sometimes I relate it, is kind of like fire. If you're very far away from the fire, you don't feel much heat. When you're right up to it, you feel a lot. So it's that feel that I'm trying to get across. Now in for electric fields, electric fields have electric field lines. Positive charges have lines that go outward. Negative charges or charge have lines that go inward. So for a positive charge, their electric field lines look like this. They go outward. We don't draw all of them because then it would just fill up with electric field lines. For negative charges, the electric field lines go inward. And what is the true what's the way to remember which direction should you draw your electric field lines? The lines always point in the direction that a positive charge would move if it started from rest. The lines always point in the direction that a positive charge would move if it started from rest. So if I'm a positive charge here, light charges repel. So the force on that charge would be away from the charge, and because of the relationship of it to the charge, it would move away into the left. If I put that positive charge over here, it would move away into the right. If I put it down here, it would go down. Positive charges are attracted to negative charges. So if I put this charge over on the left, rather than it going away, it would go towards. If I put it on the right, it moves left. If I put it below, it moves up. Likewise, the lines always point in the direction that a negative, or point in the direction in the opposite direction. I'm trying to get the English working right. The opposite direction that a negative charge would move if it started from rest. I know, horrible writing. So let's go over this again. Positive charge, if you release it, will move along the electric field line. If we have a positive charge, so the electric field lines look like this, etc. If I put a negative charge, that force that it feels will be in this direction, and it is opposite of that electric field line. So putting it to the left would make it go to the right. Putting it on the right would make it go to the left. Likewise with the negative. Electric field lines look like this. So if I put a negative charge here, it's repulsed. Its force is in that direction, though the E field is in the opposite direction. So the electric field forces show where positive charges go and they show the opposite direction of where electric fields go. This is where this is beginning to build upon all of those weeks where I spoke to you and said, don't let the calculator tell you what to do. I want you to tell the calculator what to do. I want your logic, I want your knowledge to supersede that of what a machine says. So this is where things are starting to go with, there's no calculator really as far as you're concerned that can figure this out. Let your brain do it. Let that 3-pound gland between your ears do it, because it's quite capable. So as a simple example, 214 builds on the knowledge of 213. There are things in that problem set where you're going to have to know, oh, I'm going to have to go back and figure out how springs work. Oh, I have to go and figure out how gravity and all that stuff deals with this. This is definitely a class where you will not just wipe the slate clean and just build new. You've got to remember the things from the previous semester. And as a simple example, what I'm going to do, now you know I only kill celebrities, I don't kill animals. However, I do annoy them from time to time. So let's just say in this universe, or we've walked into the room, and I need to get the prop. I need to get a prop. This is, work with me here. This is a little kitten. Now you come into the room and a little kitten is just hanging there. Not on a noose, it's just in space. It's on the planet Earth, it's just hanging there. Now, what forces are working on this kitten? Gravity, obviously. So we have this cat. Don't make fun of my cat. So the cat is purring perfectly at ease, not suffering in any way, just completely mystified that it is levitating in the middle of the room. So we've identified that there is a force of gravity pulling down on that cat. So what is that force of gravity on the cat? What two quantities do I need to know? The mass and what else? That gravity value. And we're still living in the world where gravity is 10 meters per second per second. And it's down. So when we sum up our forces, it'll be 0. And this part would be negative. But I've told you that the cat is levitating. So there are forces when everything balances out. Sum of the forces in y is equal to 0. So this is minus mg, and there's something else that has to be positive. Now, It's not on a surface. There is no normal force. But that would add an interesting part to the problem. We'll worry about that later. It's levitating. So what have we been talking about for the last week and a half? There's an electric force going on. There's a Coulomb's law force. There is, more importantly, a force caused by an electric field, which is the charge times E. Sometimes I write it like this. Really, once again, this is the magnitude. Since it is, in order for the cat to levitate, that electric force has to be pointed up. It has to. Otherwise, if it was pointed down, that cat would just boom. Now, granted, all cats land on their feet, and it'd be fine. Though, just as a side note, a common joke for an eternal motion machine, buttered toast always lands buttered side down. So if you strap a piece of buttered toast to the back of a cat, and the cat always lands feet down, and then you drop the cat, what would happen? It would just sit there and spin forever, and then you would just tap into that power and solve all the world's problems. But this cat has no toast on it, so it must have an electric field pulling up on that cat. So QE, which means that mg is QE, and the electric field in the room is mg over q. Now, I'm not familiar with kitten masses. In kilograms, what's a typical mass of a cat? 5 kilograms? Is that heavy? 5 pounds? No, that's like a 10-pound cat. Let's say 3. It's not quite a kitten, and it's not quite an adult. Let's not get into a debate about cats. And now we are in a debate about cat mass. The charge has 300 microcoulomb, so it's 300 times 10 to the negative 6th, which means that, oh, the math works out really well, that the electric field is 10 to the 6th newtons per coulomb. That's the magnitude of the electric field. Now, one of the questions is, do you have, did I give you enough information to determine the direction of the E field? Question?
Wouldn't it be to the fifth?
Yeah.
1 over 10 to the negative 6?
No, 30 over 300 times.
Yeah, 30 divided by 3.
Oh, 30, oh, blah, blah, blah. So, okay. I can't do math. Thank you. So 10 to the 5th, right? Okay. I saw the 3 and the 10 and I immediately thought 300. So the electric field is 10 to the 5th newtons per coulomb. Did I give you all the information to help you determine the direction of the E field? Eventually it's got to be up. Well, when I gave you Q, if I said the magnitude of the charge of the cat was 300 microcoulombs, would you have enough information at that point to identify the direction of the E field? If it's the magnitude. If I said it was magnitude, I never told you if it was negative or positive. If the cat was a negatively charged or positively charged. If I don't give you the charge polarity, you don't have that information. If the cat was positive, it needs a force from the electric field that's up. If it is negative, it still needs an electric force that's up. So what electric field direction would cause a positive charge to move upwards? Give me the direction of the line. So the electric field line, would it look like this or this? That or that? It would be the left one. Because positive charges always feel forces in the same direction that the electric field does. Is it up or down if it's a negative charge. It's down. Electric charges that are negative feel forces that are in the opposite direction. So if we have a charge like this, and let's turn off gravity for a moment. Positively charged, the electric field causes it to start doing this and accelerating in that direction. Which direction is the electric field? Hold on. Was I just like mouthing words? Let's repeat. A charge, positively charged, I let go. It starts moving in this direction. In which direction is the electric field at that point? I said positive charge, it has to go in that direction. Huh? Electric field is always is magnitude. So the electric field vector has to point in this direction for a positive charge to move in this direction. If this was a negatively charged, electric field is in this direction, it would start moving in that direction. Now this brings up an interesting part of the problem. In 213 physics, if there was only gravity, that would happen. It would just drop. And what did I tell you about those equations of motion? That there is no horizontal acceleration in the experiment. Well, now, there will be. In this particular problem that we're going to do, you have a room. Now, what we're kind of building up towards is, before we really get into the experiment,
So are you saying we do have enough information now to determine?
well, if I said that the charge was, if the cat was negatively charged, the electric field would be going down. If it was a positively charged cat, the electric field would be going up.
So if you don't tell us that we don't.
If I don't give you the specific polarity of the cat, you have no idea. And then the answer would be not enough information. Now, in our world that we're building, electric fields can be generated in all sorts of ways. You can have a charge, and then you can have a point a certain distance away from that charge, and it has a particular value in a direction. Or we could have a capacitor, and the advantage that having a capacitor, and it's similar to the examples that I did just a few minutes ago, is in a capacitor, which really are two charged plates. We'll go into detail, we'll go into more detail about this later, but the advantage of a capacitor is that the E field is uniform. If the electric field at that point was 200 newtons per coulomb to the right, it would be 200 newtons per coulomb to the right at that point. The advantage of a capacitor is that the E field doesn't change within the plates of the capacitor. For point charges, since the E field is based on distance, the further you get away from a charge, the smaller the E field gets. So the further away you get from something, the smaller the electric field. One of the reasons why we do this particular type of problem, is that we don't have to consider a changing E field. If we had a changing E field, there would be a far greater need for, shield your ears for an offensive word, calculus. Yes?
So why the capacitor or the arrows going in the same direction when the positive is on one side and the negative is on the
Well, really what I'm showing here is that this is a positively charged plate, deficit of electrons. This is a negatively charged plate, an excess of electrons. It sets up an electric field between those two plates of a constant E field magnitude and direction. And so in this particular experiment, we don't know it, but this side of the room has a type of charge, and that side of the room has an opposite charge. We are in a human-sized capacitor, which would be fairly an unusual event. So that side of the room has one charge, that side of the room has an opposite charge. There's an electric field in the room. If we know what that electric field value is here, we know it there, we know it where you sit, we know it where you sit, we know what it is in the back of the room, we know its direction and magnitude. So we have a mass. It is 20 grams. It is a charge of positive 50 microcoulombs. Is dropped from a height of 3 meters. So this distance here is 3 meters. So when I say dropped, for those of you who have not taken my course for 213, be educated by the 214 students who should know, that have taken my 213 course. What does the word drop imply? No initial motion. The V naught in both directions, V naught X and V naught Y, is equal to 0 meters per second. That is the definition for dropped. So when this thing lets go, there are no forces. Now, well, there are forces. We are on the planet Earth, which means gravity is down, and it has a magnitude of 10 meters per second squared. I'll tell you that the only other thing that could affect this thing is an electric field. Because what this thing does is it lands 2 meters away. So you have something, you drop it, it starts to go in another direction and lands. If there was only gravity, it would just fall straight down to the ground. If there was an additional force, it does what it's doing right now. The E field, now the way that I could make this just a horrible, horrible thing is I could have the E field acting at a weird angle. But right now I'm going to tell you that the E field is either to the left or to the right. Now, from just that information alone, the fact that the E field is to the left or to the right, and the fact that the charge is positive, what direction is the E field? It's to the right. Why?
Because it's positive.
Because it's a positive charge and
It goes in the same direction.
it moved to the right. So if the electric field was to the left and that was a positive charge, it would have moved to the left. But since it's a positive charge and it moves to the right, the electric field must be to the right. Now the question that I have for you is, what is the magnitude of that E field? And what we're doing is we're working on a variant of the two-dimensional motion problem that we did in lab. We have the advantage of knowing that it was dropped, which means that the initial velocity in both x and y are 0. You also know that there are no vertical electric forces. It's all horizontal. Why all horizontal? Because I say so. If I made it at a weird angle, it'd just be nightmarish. So, in the vertical, what is the only force acting on that object? Gravity. So we have a standard y equals y naught plus v naught y t plus 1/2 at squared, where the acceleration is -10. Or you could just say -g, but we're going to use -10. V naught y is 0. Y final is 0. Once again, when you set up your equations, make sure that you use my favorite number. Initially, I felt that I had no favorite numbers, and someone challenged me and said, yes, Dr. Eschenberg, you do. I say, how blasphemous, how dare you say such things? And he goes, your favorite number is 0. And I'm like, that's a very good point. Because 0 gets rid of so many problems. Do not plug in numbers unless it's 0. Always plug in 0. Makes things go more simply. I know A, -10. I know y naught, it's 3. Solve for t.
I have a question.
Mm-hmm.
How do you know the positive force is going right because it's attracted to positive, or if it's going right because it's repelling from a negative force? Do you know what I'm saying?
It all depends on a couple of quantities. First, it's a positive charge. Second, I know that positive charges move along electric field lines in the direction of that electric field. So because this particle, which is positive, moved to the right, there had to have been an electric field to the right. An electric field direction to the right. And now it gets into all sorts of potential types of problems. So positive electric field, forces to the right. Positive, forces to the left. Charge negative, force to the left. Charge negative, force to the right. In all these cases, the positive charges are moving in the direction of the electric field. In a way, we'll introduce a new term. The vectors are parallel. They're in the same direction, they're side by side. This, which is what the negative charges are doing, it's called anti-parallel. They're of the same magnitude but opposite directions, and they still don't touch. So it's kind of, those are two words that help describe. Positive charges are parallel to their electric fields. Negative charges are anti-parallel to their electric fields. Anti-parallel meaning they go in the opposite direction. Parallel meaning they go in the same direction. It's just the behavior of what the positive and negative charges do.
So this the Y on the problem that we're doing now, that we started off with, that one, why is that one 0 and not the Y not? Okay, so what is Y not?
Y naught is the initial Y position.
Okay.
It comes from my favorite equation. Final position is initial position plus V naught T plus 1/2 AT squared. It's the equation of motion. We have this. So the time, -2, Y naught 3, A -10. It's the square root of 0.6. So 0.77 seconds. And that's the time that it took for it to fall.
That beats 0.6.
6 divided by 10 is 0.6. Square root of 0.6. 0.77. Ah, sometimes I am right. Yeah. I mean, blind squirrels in forests find a nut eventually, so. And I'm the blind squirrel in that joke. So that's the time that it takes for it to drop. Since the electric field was not acting in the vertical, only gravity, this is a basic 213 problem. Now it gets a little bit more interesting because X, its equation of motion for 213 looked like this. But now we add that to it. It looks like the Y equation because there is a horizontal acceleration. First thing we do, plug in our zeros. The X position and the horizontal velocity are now part of the problem. And by part of the problem, it gets rid of the problem. We're left with X equals 1/2 AX T squared. I know X, that was given, 2. I know T, we've just determined that, 0.77. We now have to figure out what A is. Force is mass times acceleration. That's Newton's second law. But force also can be expressed as the charge times the electric field, as we've used before. As we used before in the levitating kitten problem. So if force is equal to MA and MA is equal to QE, then A is QE over M. And I can rewrite this as 1/2 QE over M T squared. We substituted in. Since I didn't know what the horizontal acceleration was, I could substitute it in. Now that we have this, solve for E. 2mx over qt squared. The 2m come up, the qt squared go down, and that is equal to E. Now I've just threw in the numbers together, so hopefully we'll get something that's not totally annoying. 20 grams becomes 20 times 10 to the negative 3. X becomes 2. Q becomes 50 times 10 to the negative 6. T becomes 0.77 squared.
For the 20, you gave it to us in grams. Do we need to convert it to kilograms?
Yes. And once I get my stuff together, I'll talk about that. All right, someone double check the math for me. I get effectively 2,700 newtons per coulomb. 2698.6. So do we get that? Is that confirmed? Calculator girl. Am I missing? Oh, calculator girl isn't even in the room.
She overslept.
Huh?
She overslept.
She overslept? Do I have confirmation from the human calculator, from supercalculator woman? Is it 2698?
It's close enough.
It's close enough, yeah. So, once again, let's talk more about Eschenberg pedagogy or philosophy on teaching. This is physics class. This is not accounting. This is not math. It is physics. I'm more interested in the equations and your understanding of it than your ability to type in a calculator. So to get in the 2700 range, so from 2698 to 2701, I'd be fine with.
Where did you get Q?
Where did I get Q? Q was given.
Okay.
It was given because I say so. Now, it's one of those things where it's like, it could have been, and this is one of the great things, your ability to get that equation together means that I have to give you everything but one of those variables. You should have the ability to manipulate this equation, solve for time, mass, position, charge, electric field, any of those. And that's one of the primary goals for this class, manipulation of variables. Someone had a question over here on this side. All right. Any questions about this? Yes. Okay. This is one of the reasons why homework is not due until the 3rd week. This is one of the reasons why we have a little over a month for the first test. Because all of you just have that deer in headlights look. And I am perfectly fine with that. We're not leaving for another 11 minutes, so don't start packing. Or you start packing, I start dropping. Okay. Not always. Oh, let me address her question. If it gets to 9, 10, and it gets to a point where I know I can't do another problem, we'll leave then. So no one pack. Okay, it's getting quiet again. You're just getting us. Okay. Yes.
Okay, so I got it. So when we did FE equals QE, Q is the magnitude and E is the electric force,
Electric field.
electric field.
Electric field value. All right, so let's get this. I think this will be enough to close out the lecture. When I give you, as one of the students over here noted, I gave the mass in milligrams. The unit that you should always use in these equations is kilograms, so you need to do that conversion. For time, seconds. For distance or volume or area, it needs to be in multiples of meters. Now that we're dealing with charge, it has to be in units of Coulomb. So when I said,
Is that a capital?
it's a capital C. I forget what lowercase c is, but yeah, it's the big C. So when I said 50 microcoulombs, 50 microcoulombs, you should convert that to 50 times 10 to the negative 6 coulombs. So you need to have a knowledge of milli, micro, nano. That's about as far as we're going to go on one side. Kilo, mega, giga on the other. So know those basic conversions. The only thing that I'll introduce. So any more questions on this? Yes. Typically what I try to do is lowercase q can be positive or, oh, and I really hate saying this, positive or negative. It's almost, the negative signs are not used as much as the positive sides. If I use positive Q, that is always positive. I'm very hesitant to have equations that have negative signs in them because negative signs are shifty. One of the things that that we know is G is the magnitude of the acceleration by gravity, which is positive 10, and A, which is the acceleration of an object falling to Earth, is negative 10 meters per second squared. So it is kind of a, I tend to deal only with positive as far as I can, for 95% of what I do. There are a few exceptions, but there are a few. Okay, does that answer, that answers that. All right, so we got 2 more minutes, which really will mean only, I'm gonna say this one sentence and then we'll split. Next time, Thursday, the discussion will be about potential energy, or volts. That's it. You guys can pack up and go.
Are we just following the